Yeah.
All right, now this is the fact that we already have an existing magnetic field, but ultimately, how do we create a magnetic field? Well, magnetic fields are created by moving charge. So we can have a charge moving, creating a magnetic field, and we have a second moving charge running through it, and suddenly it's affected. Not affected, they'll affect each other. So we have, don't jump into that quite yet. Basically, a magnetic field is created by, well, there's something known as the Biot-Savart Law. And it's pronounced Biot-Savart. And I'll make sure I get the right things in the right place here. I'm going to jump ahead a chapter. Wow, it's just one of those days. Yeah, it should be. Bunch of variations on this one. I don't even have it written down there. No. I guess I have eliminated it from it. That's a 252 thing. I was going to introduce a second physics equation. It was going to be exciting. And nope. All right. All right, there's something known as Biot-Savart's law. I cannot do it off of my memory at the moment, so. Hold that thought. Glad to be immortalizing this.
Could have looked it up.
So it is a calculus formula, so I just want to introduce it. It's equal to u naught over 4 pi times the non-calculus formula times a charge v cross r over r cubed. Which is one of the reasons why this is the magnetic field that is created by a charge that is moving at some velocity v. And this is the force from a magnetic field that's on a separate charge. And so you can hopefully see why with electricity we had a nice little formula. I have two charges, here's the force between them. But it gets far more complicated when you start dealing with this because you have to have, in essence, two charges moving relative to each other. And actually, you have to have two charges moving relative to each other and to the observer. Now, dot, 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 throw a lot of calculus in there. And we come down to, if I take the magnetic field along a particular loop, the circle meaning that we're doing a loop, the fact that we're going to start at some place and end at some place, that's going to be equal to this mu sub naught, which shows up here, and actually I don't know if we brought it up on Monday, times the current running through it. This is known as Amperes Law. This is actually the, I've mentioned before, of Maxwell's equations. The first of Maxwell's equations is if I do the sum of the electric field times the area around a closed surface, that's going to be equal to the enclosed charge over epsilon sub naught. If I do the same thing with the magnetic flux, so B dot A, that's equal to 0. And now we have the sum along a line. The first two are areas, the next two are lines. B dot delta L, that's equal to mu naught I. Obviously, I'm presenting it without derivation. This is not a complete law. We need to do some more before we add in the final term. But this is sort of the next big step. So for example, if I have a current flowing out of the board right here, and I look at a circle there, and I'm going to try to actually draw a circle. Excuse my back. I'm not sure that's better, but we're going with it anyway. So I have some current flowing out of the middle of this circle here. It does create a magnetic field. The direction of the magnetic field is, well, current's flowing this way. We have yet one more right-hand rule. It's like put your thumb in the direction of the current and your right thumb. And then your fingers curl in the direction of the magnetic field. So the current coming this way will create a magnetic field going around in that direction. So if I look at the magnetic field, first off, if this is the center of if the current's in the center of the circle, there's no reason why the magnetic field would be any different at any place. The magnetic field strength would be any different anywhere. There's no favoritism towards one side or the other if all I have is just a current flowing out the middle of the circle. So the strength of the magnetic field should be the same all along here. In essence, what happens here is this just becomes B to the dot product of the sum of delta L. In other words, the magnetic field times the length here. And what's the length along a circle called?
Circumference.
And so this becomes B times 2 pi r. Because we're going to do our length in the same direction as the magnetic field. And that should be equal to mu naught times I. And so the magnetic field that is created by a current is mu naught I over 2 pi r. Sort of a direct result of Amperes Law. Notice the way I've written the problem right here, there's no vector symbol over the B. To find the direction, you use right-hand rule. And so the direction of the B field, use the right-hand rule. All right, mu sub naught. This has an exact value in SI units. 4 pi times 10 to the negative 7th Tesla meters per ampere. Which ends up being 1.2 something times 10 to the negative 6th. So if you notice on Biot-Savart, since we divide mu naught by 4 pi, that 4 pi immediately goes away. And so it'll just be this times 10 to the negative 7th. So now, I have a current flowing down that way and a current flowing down that way. And I call this I1 and I2. And the question is, what is the force on wire 1? What is the force acting on this wire right here? Well, they're both creating magnetic fields, but I1 is not creating a magnetic field that's acting on itself. That would violate Newton's third law. So, all right, so this current I2, which way is the magnetic field going here because of this current on this side? Not, is that you're answering the force or the direction of the magnetic field? Yeah, you're a little off there. So, which, right-hand rule. So you were doing the right-hand rule there.
Into the board.
So we just said it?
Into the board.
Yeah, so if the current's flowing that way, at that point it's going into the board.
Oh.
In the bathroom, it's going that way, and where you are, or I guess where Carly is, it's going that way. So the magnetic field is flowing around like that. So at this point, the magnetic field is into the board. This is the magnetic field from 2. I know that the force on this wire here is represented by this. I'm just going to go ahead and, for this specific problem, and for most problems like this magnetic field is perpendicular to the current. And so the force on 1 is going to just be the current of 1 times the length of 1 times the magnetic field from 2. They're already perpendicular, so the cross product is just the magnitude of the cross product is just the product of the magnitudes. I know the magnetic field created by 2. We wrote the formula over there. So this becomes I1L times U naught I2 over 2 pi times, well, the distance between them. We call that probably R. And so we can take this and put it in a more familiar form, or at least a more book familiar form. That the force on 1 per length is going to be equal to mu naught I1, I2 over 2 pi times the distance between them. And it usually is presented in terms of force per length. So, what is the direction of this force? We have a magnitude here, but what's the direction?
So the force acting on I1?
Yeah, on wire 1, yeah. This flashes back to the stuff we did on Monday. Did you get that? All right, so you're using a right-hand rule, which you should. What your next, you're doing.
Because the current's going down, and then the gravity, or the magnetic field is going into the board, so then this one's
The magnetic field is going into the board.
Sorry,
Finger points in the direction of the current, the index finger.
Oh. Oh, fudge. Out the point?
Force goes that way?
All right, so we have various fingers here. Sorry, so the index finger in the direction of the current. Magnetic field are the multiple fingers here. Thumb points in the direction of the force. The hammer,
Oh, you're right.
the
yeah.
thing that forces the reaction that causes the bullet to shoot out. It is indeed forced that way. So finger down, magnetic field into the board. Magnetic field in, yeah, there you go.
Okay, see, I was thinking still the clockwise
Yeah.
thing, so what is this?
Yeah, because it's here. If the, you know, we can put this wire in a different spot.
Wait. So then,
So,
Wait, was someone about to ask a question over here?
oh yeah.
All right, ciao.
Okay, so the right hand rule on Monday, so the index means for the current, this is for the gravitational, not magnetic,
Magnetic field,
and this is
the force.
the force, okay.
Right-hand rule also works for, oh, we can do it a different way for those who are just fans of cross products. L cross B, L is down, B is into the board, so L cross B is in that direction. Or you can picture positive charges flowing with some velocity down using this one. Then we have V cross B, still that way. Or right-hand rule, V, B, and then the force in that direction. What's the magnitude of the force acting on wire 2? And what is the direction?
Direction of the force?
Yeah,
Magnitude is into the board.
that's a direction into the,
Yeah.
direction is not into the board, not of the,
To the right.
not of the direction of the force is not into the board.
Left. That's the direction.
Okay. So direction would be that way. What's the magnitude?
Would it be the same as the first one?
So you're saying they exert a force on each other that's equal in magnitude but opposite in direction? Is that what you're claiming?
Yes.
Huh.
Yeah.
Only we'd seen that before somewhere.
Oh man.
Yeah, you could do right-hand rule to figure out the direction. The magnetic field that one is creating, current's going that way, so the magnetic field here is coming out of the board. So we have a magnetic field from wire 1 out of, oops, sorry, out of the board, wrong symbol, out of the board. So magnetic field's coming out, current's going down, the force would be the other way, or just employ Newton's third law, and they should be going in the same direction. If they weren't going in the same direction, then you could just take 2 wires, put a current through them, and you can get them just to start moving. Or moving, depending on which way you have it. They actually would come towards each other. If the currents were going in opposite directions, what would happen?
Explosion.
So far, not that violent. If the currents were going in opposite directions,
Why did they just flip the direction of?
so therefore, what would happen to the wires?
Go apart from each other.
Turned it, well, not turned it down. They just like go on. In the opposite direction?
The force would be in the opposite direction, so if I have 2 wires side by side, what potentially could you see? Yeah, because now if they're in the same direction, you could see them come together if they're light enough, or if they're not light enough going in the opposite direction. So all we need is a wire that's light enough, or some conductor that's light enough in order to make that happen. And we've got that.
No way.
Yes, wait, this is a lab. It's probably my favorite lab, even though the results suck.
Nice.
One of my favorite labs, I guess I should say. So we need a power supply. First time I did this, I didn't have power supplies. I was at CPCC. And so what I ended up doing was just stringing 20 batteries together. The downside of the batteries, it worked. The downside of the batteries is if there's a small little gap between any 2 batteries, then it just won't work. So you have to really make sure they're jammed together. And we need something light enough. And here is our wire. Pretty flat. Now, since this is a force per length, you can do it with smaller ones, but you can get a more dramatic effect by having a longer piece there. And you want them to be as parallel as possible without actually touching. If they touch, so if they're touching up here, then basically as the current runs through it, it's going to short circuit, it's going to go through there, and you won't get any current through here. So you're going to need to have them separated so that you can have a current. We're going to flow current down one side and up the other. So the current will be going in opposite directions for most of it. Down at the bottom it's going to be a little bit different. We also need to somehow drape them so that they will do this. And what I've done in the past is use chairs. So there might be some moving around here. And apologies to those in the front row. I should be able to clear some space here. So move it back. I assume that the squealing out there is because they're thinking, he's about to do that demonstration.
You don't.
All right, should be sufficient there. And tape.
Yeah, I try to get it to you.
Did I mess up again? I did. I think I had it right the first time. There we go. Small little pinch at the bottom, hopefully. And then try to bring this closer together. First couple times I did it, it worked beautifully. Everyone could clearly see there was this puff. Then I went through about a 3-year period in which it just failed miserably every single time. It was more like twitch. You know, one of those points where you're going, was that just the air conditioning that moved it? And then there was one particular class I was doing it, and it basically did the twitch, and I was just frustrated because I knew it had worked before. And so I just turned it around, you know, flipped it around, so from the shiny side on the inside to dull, or one of the way or the other, and it worked beautifully. So I have no idea why that makes a difference. It's definitely not the conductivity. The dull side, shiny side is just the way it comes off the aluminum press. We need to be able to hook up this thing. So we'll grab our wires. And it looks like some has some alligator hooks already, so we're good there. We're going to use DC because we want the current to be steady going one way or the other. I think it was AC, since it's the current's oscillating back and forth 60 cycles a second. I suspect what would happen to it, the thing would just sort of twitch. Although I haven't tried it.
I think we should.
We might should. Is it a long one here? That's a probe, that doesn't go in there. This is turned off, right? Yeah. Now, one thing about this is because this is just an aluminum strip of particular length, remember that resistance depends upon resistivity times the length divided by the area. There's not a lot of area there, it's a flat piece of aluminum foil, and the distance isn't very long. And so, primarily because of the length, there's not a lot of resistance, and so we are going to quickly trip the breaker in this. So it's just that we can easily reset it, but that is an issue so it won't be sustained. But because of that, it'll puff out, and then this thing, you'll hear a click, and it'll collapse again. And as we reset it, it'll puff out, and so we can have a little bit more control. It should be slightly more dynamic than if we had something with a large enough current. And I'm trusting all these wires are good. Now, if you look at this right here, we have the red and the blue current, and this is DC, direct current. This current will flow out of the red here, and it will flow back into here. So the current's flowing out this wire, down this wire, across here. It's going to be flowing down this side, up this side. Not that it should make any difference if we flip it. And let's crank that all the way up. Please work. There we go. I need to reset it. There we go. And so lending some credence to what we just talked about. And that was indeed the kind of dynamic that I want. Are they touching right there? Separate them slightly. Is it alive? So, a lot of setup time, but to me it's worth it. A physics demonstration that works, they happen rarely, so it's nice when it does work.
Just try it, the AC current.
Oh, that's right, we're gonna try to see. Don't want them touching up there. Now with AC, since current's flowing back and forth, you can't, when we do the AC lab, I will ask you to make an assumption that current's flowing out of one side or the other, just because if you are inconsistent with that, then you're gonna be off by what the formula is by 180 degrees somewhere. And so it's useful to pretend current flows out of one side or the other. But since current does not flow out of one side or the other, it's flipping back and forth, they're the same color. That's another way you can tell DC from AC besides just the labels on it. Oh, that worked just as well. I guess we need to give it some time to reset.
Interesting.
I don't know why I've never tried the AC before.
Because Chow wasn't here.
That could be it. I was waiting for this moment. And that, is that the next lab we do? The next lab is either, next lab probably will be, down here. 152, this is us. The lab here, this is probably gonna be a plain old resistor lab. This would probably come in the week after spring break. Now, recognize that current's flowing down one side and up the other. If I had switched the leads on the DC, it would have just, instead of flowing down this side and up that side, it would have gone down this side and up that side. So you should have gotten the same effect. There was a group sitting back there, of course, in the first area, where they would turn it on and the two sides of the aluminum foil would come inside, go in. Only time I've seen that, it would go in. And so I went back there trying to figure out what was going on because, again, Nobel Prize or something. And what I did is I just switched the leads, so instead of going like this, it went like that, and it worked. I had a former student who's studying electrical engineering at NC State stop by, and I posed this to him, and he couldn't figure it out either. So I asked him if he could, he was going to look into that. I have not heard back. I have a speculation that there was a bend in the wire, bend in the aluminum foil somewhere, which caused it, but. Yeah, the curse seems to be the easiest explanation. Any questions before I take it all apart? Any questions? So we have like done stuff.
Yeah, just in case. I don't think you
All right, guess that's chapter 22.
What is the name of that movie that your daughter?
Code 8.
Code 8.
Yes.
Yeah.
Are there only the two equations?
I guess people get crazy. They probably.
Well, we introduced, and so those are the only two equations from the first part. There's also the torque, not that we do much with it, but we went through the derivation the other day. That's the magnetic dipole moment across the magnetic field. Then we have the B dot delta L, this equation right here. And then specifically for a current carrying wire, magnetic field is equal to E naught I over 2 pi R. That's the magnitude of it. And then this one. I guess we've had 3 physics equations. We've had Coulomb's law, this force equation here, and then Biot-Savart. 3 physics equations. And that might be the last of the physics equations for the rest of the course. The rest is just math.
Yes. It's both.
This is which was.
All right. Picture yourself, first half of the 19th century.
So what?
You are incredibly wealthy because those are the only people who are doing science because they could afford to do it.